Okay, so today, like I said, we're going to be doing section 7.6 over inverse trigonometric functions. And you can see how we're going to get started. We're going to talk about the sine function that we all know, and then we're going to talk about the inverse sine function to get started today. Before I start filling out any of my notes here, I want to switch over to a graphing tool just so that we can make sure we understand what's going on. So here's desmos.com, and I can graph a simple sine function just by typing it in. Let's just zoom in a little bit on the y-axis. Okay, so we don't need to include quite so much on the x-axis either. Maybe just -8 up to 8. Okay, so here is a sine function that we all know and love, or maybe hate, depending on your feelings. But we know its general shape. It starts at 0. When you plug in 0, then it goes up to 1. When you plug in pi over 2, and then back to 0 at pi, -1 at 3 pi over 2, and then back to 0 at 2 pi. And then that will repeat that cycle. And this is related. You might be able to see my little screen still, hopefully. This is related, of course, to the unit circle. We know that sine is the vertical coordinate of the point on the unit circle corresponding to your angle. So if you start over here at angle 0, you of course start at 0, and then you go around all the way around the circle to 2 pi, and then that'll just keep on repeating. So every time you go around the circle, you go 2 pi, you'll repeat the pattern of sine. So this is clear from the graph. It's a repeating periodic function. It looks like a wave, right? But my point here is that for inverse functions, we're going to have to restrict the domain of sine. You might recall that inverse functions need to come from a one-to-one function. And after I write this word, I'll remind you the test for one-to-one is the horizontal line test. And if we move back over to the graph, you can see that if I draw a horizontal line anywhere, and maybe I can just graph one since we have this convenient tool. That's not gonna work. Will that work? No. Okay, so here's just a single horizontal line. I was hoping to put a slider in, but it wasn't cooperating. So if I draw in a line at y equals a half, a horizontal line, then we're of course going to cross the graph multiple times. So what we need to do is restrict the domain, the things that we're plugging in to our original function. Let's see, I need a less than or equal to sign. And we need a minus sign. Okay, so what I'm going to do, you can see I've put in a slider on my domain. So I'm restricting the things that I can plug in for x to values between -a and +a. And if I increase this all the way up to 10, it looks the same as it did before I added the slider. And what I need to do is get rid of enough of my curve so that this horizontal line will only cross the curve once. So let's just see if we can do that by decreasing the value of A. So you can see how it's getting rid of some of my curve. I still haven't gone far enough. And it looks like at this point, I've gone far enough to not cross that line that I drew in twice. But if I put in another line at maybe 0.75, you can see that we're still haven't reduced it quite enough. So let's keep on going. Or maybe we're good now. Let's check. Maybe this line. No, not enough yet. Let's keep that going. And that's about the value. This isn't exactly right. I'll tell you the exact value in just a second. But once I've decreased my A to 1.5, we can see that none of these lines that I've drawn are going to cross it more than once. And we can put in maybe another one, 0.99. This line only crosses once. But to be totally precise, the number that I have to plug in for A is actually pi over 2. Okay, so pi over 2 is just a little bit more than 1.5. It's 1.57 and then a continuing decimal. And so if I draw any horizontal lines across this, we're only going to hit the graph once. And you can see I'm going from minus pi over 2 up to pi over 2. And back on the unit circle, that corresponds to the right half. So down here at the bottom, all the way up to the top at pi over 2. Okay. So are there any questions before I turn my graph off? Or maybe I'll leave it up there, actually. Are there any questions? Okay, so now that we've got a one-to-one function that passes the horizontal line test, we know that it has an inverse function. That's something that we learned a few weeks ago. And the way inverse functions work is that they flip the graph across the line y equals x. So this blue one that I just put in. Let's see. There we go. Make that into a dashed line. Help with visibility. Okay, so sine inverse is usually called arc cosine. Or, excuse me, I'm getting ahead of myself. It's called arc sine. So you can write it two ways. You can put a minus sign in the exponent to represent an inverse. But this could be a little dangerous because there could be confusion about whether you mean an actual exponent. So a -1 exponent would flip it to the denominator, or whether you mean an inverse function, which, as we know, swaps our x and y values from our original function. So if you think there's ever going to be any confusion, it's a good idea just to write out arc sine instead of this way, sine inverse. So let's go ahead and graph that. Arc sine of x. And we can see it here, and maybe I will change this one also to something. There we go. Make the curve a little bit more obvious. Maybe make it darker. So this black curve is arc sine, and all it does is it flips the values of the red curve, the regular sine function, across this one, y equals x. Okay, and one thing to note is the domain and range of this function. They swap the domain and the range of our sine function. So you can see it, only certain values of x can be plugged in, and only certain values of y will ever come out of arc sine. Now I really do need to switch back to my paper so I can write some of those details down. So we're restricting the domain of sine to minus pi over 2 up to positive pi over 2. And here I'm just using interval notation. The brackets mean I'm including the endpoints. And we know what our function looked like. You can just sketch it in on your paper if you want. Something like this. Just a regular sine curve where I've chopped it off. And then arc sine mirrors this across the line y equals x through here. So the x values and the y values get swapped. So that means the point pi 1, this one, becomes 1 pi up here. And this other endpoint at minus pi over 2 minus 1 becomes the point minus 1 minus pi over 2, which is down here. And 0, 0 doesn't go anywhere. And then we can see how these get switched. Maybe I'll switch back to the graph really fast. So the black curve, remember, is arc sine. So I'm going to connect mine on my paper, something like this. So these are the graphs for sine and arc sine. Are there any questions so far about what we're doing? Thinking about the inverse functions? Okay. So the takeaway here is that we're only allowed to plug in certain numbers into arc sine. So the domain and the range of our original sine function were minus pi over 2 up to pi over 2. And then the range we can read off the graph is from minus 1 up to positive 1. And then the arc sine, the inverse function, is going to swap those. The values that we can plug in are between minus 1 and 1. And the values that come out, the possible angles that come out, are between minus pi over 2 and pi over 2. That's going to be important a bit later when we try to plug in numbers into arc sine. But before we do that, I want to go ahead and talk about arc cosine. And it'll work pretty similarly. We're still talking about the unit circle, essentially. And we know that cosine is the x coordinate on the unit circle. Let's see, scoot that down just a little bit. X corresponds to cosine. So as we move around the unit circle, we're going to get repeated values for cosine. That means it's not going to be a one-to-one function either, which we can easily see if we move back to the graph and just plot cosine x. So we can see it repeats. And we want to think about how we can restrict the domain, the x values, to get a one-to-one function. But for cosine, we're going to do something slightly different. We're going to start at 0 and then go up from there. So here is the maximum value. If we start at 0, we can see that this doesn't restrict the domain quite enough, because if I put in a horizontal line, it's going to cross, well, 3 times in this case. So I need to restrict at least this much so that it no longer crosses my horizontal line twice. But if I plot one in at minus y equals minus a half, we can see we still have problems. So we need to keep on reducing. Oops, that's the wrong value. We need to continue reducing. And this is still not quite far enough. So keep reducing a little bit. And that's where we can stop. If I move one of these sliders up and down, we're never going to cross the remaining segments of cosine more than once. Okay. But 3.1, that might be a familiar number, or pretty close to a familiar number that you know. It's actually going to be pi that we need. So we're going to restrict the domain from 0 to pi. That corresponds to the upper half of the unit circle back on my paper, if you can see where I'm pointing. So 0 over to pi will be our domain, and we can go ahead and plot as well this little segment of cosine. Something like this. Now let's get rid of some of this extra stuff and plot in that line y equals x, where we're going to mirror cosine. Okay, so it's going to get mirrored across this curve when I type in the inverse, which is called arc cosine. So these, let's change this color since they're the same. Make this one orange for contrast. So the values on the cosine curve, the purple one, get mirrored across the line y equals x, and they end up looking like this orange curve here. So the domain 0 to pi becomes the range 0 to pi, and the range of cosine 1 down to -1 becomes the domain of arc cosine, -1 up to +1. And I can sketch that on my paper, which hopefully you can still see. Looks something like that. Are there any questions before I close down this graph? Okay. So now on my paper, I have my cosine restricted down to the domain so that it passes the horizontal line test from 0 to pi. and then the range, the maximum value is 1, the minimum is -1. So in interval notation, we would write that this way, still including the endpoints. And then we swap the domain and range for arc cosine, excuse me. So the domain comes from the old range, -1 up to 1. And then the new range comes from the old domain, 0 up to pi. And the key takeaway from the current discussion is that the values that you can plug in to arc cosine must be between -1 and 1, inclusive. And the values that come out of arc cosine are always going to be between 0 and pi. So still no questions before I flip the page and move this? No? Okay. So most of this is probably review for you guys from your trigonometry class back in, I guess, high school, or your geometry class or pre-calc class, wherever you learned this the first time. But I want to go ahead and get some practice with these functions before we move on to trying to do calculus. So what happens if I plug in a number like 1/2 into arc sine? And this is an inverse function. So what I'm looking for is something that essentially undoes sine. So I'm looking for the value of theta that solves this function. So sine of theta equals 1/2. If I want to find arc sine of 1/2, I have to figure out what angle solves this equation. What value of theta makes sine equal to 1/2? Keeping in mind that theta, the output of my arc sine function, has to be between -1, or excuse me, it has to be between -pi/2 and pi/2. So what value of theta is a solution to this? Sine theta equals 1/2. Anyone?
Pi/4.
Okay, so pi/4, I'm just drawing a unit circle. Pi/4 would be here.
Pi/6.
And then pi/6 is down, let's see, it's a bit further down here somewhere. So pi/4, remember the coordinates on the unit circle are √2/2, and the same for the y coordinate. At pi/6, the values are √3/2 for the x coordinate, and then 1/2 for the y coordinate. The y coordinate corresponds to sine, so that one is the solution. Pi/6 is the angle that gives us 1/2 between -pi/2 and pi/2. Good. So the thing to keep in mind is that angles come out of your inverse functions, your arcsine and your arc cosine. And you'll have to remember the unit circle in order to find some of these values. Let's see. There's something I might have already said it. Something I was going to point out. Let's think about arc cosine next. So what value of theta solves this equation? We're reversing the roles of x and y. So we're looking for the angle that solves this. We actually already drew it in. Remember, cosine is the x coordinate on the unit circle. Do we already have a square root 2 over 2 on the x coordinates here?
Yes, it's pi half.
Close, pi over 4. Pi over 2 is actually the vertical here.
Yeah, no, I didn't want to pretend I was awake yet.
Got it. Oh, I remember what I was going to point out for you guys. So the important thing to remember on the unit circle is that the values get repeated. And so like this x value, the square root 2 over 2, it gets repeated over on the left side of the circle. Oh, excuse me. I was thinking of sine. The x value gets repeated down here. So this x value corresponds to this one, right? But for arc cosine, the values that can come out, the range values of arc cosine, are between 0 and pi. So whenever you give an answer for arc cosine, it always needs to be on the upper half of the circle, from 0 to the left at pi. So this will never be a solution or an output from arc cosine. What about the next one? Arcsine of minus square root 3 over 2. We're trying to solve this equation. What value of theta gives sine theta equals minus square root 3 over 2?
Pi over 6.
You're very close. Minus pi over 6 is down here. So the vertical coordinate is actually minus a half.
I missed the negative. I guess that was the whole point.
No, what I was saying is that the x coordinate is correct. You get the minus square root 3 over 2. But sine is the y coordinate, which is minus a half. Oh, okay. I think I see what you were saying. What we need to do is just go further around the unit circle down to here. Minus pi over 3. Okay. The next one is a little bit more tricky. It's not just a unit circle question. You don't just have to remember values, because now we have an arc cosine being plugged into a different trig function, plugged into a secant. And what we're going to do is, well, something you might call a triangle method in order to figure this out. So remember what arc cosine of 1/2 corresponds to is the solution to this. Oops, I need a cosine, of course. Cosine theta equals 1/2. So the output of arc cosine of 1/2 is going to be the angle that corresponds to cosine theta equals 1/2. But remember, cosine theta is actually just the adjacent side of a triangle divided by its hypotenuse, of a right triangle divided by its hypotenuse. So let's draw that triangle. It doesn't have to be to scale, so don't worry about that. Just write down what the values are. So the adjacent side is 1, the top of the fraction. The hypotenuse is 2. And theta, which maybe we could figure out, but it turns out it doesn't even matter what theta is. We can just write it in. And then secant is going to, well, we're going to find the secant of this angle, the output of arc cosine. This is theta. Okay, that's getting a little messy. Off to the side, let me remind you what secant is. So if you plug in something to secant, this is just 1/cosine. So that means it flips this. It's the hypotenuse over the adjacent side. Something like that. So what we're going to do is go to this triangle that we drew for the angle, the output of the arc cosine, and find the secant of this triangle for theta. So we find the hypotenuse, we divide by the adjacent side, which is 1. I shouldn't have written this there. That's where I need to write next. So this will give us secant of theta, and secant of theta is the hypotenuse divided by the adjacent side. So the answer is 2. So the trick, let me remind you, was to remember what cosine of theta means. So it's really just the adjacent side of a right triangle divided by its hypotenuse. And then we could use that in order to simplify the problem of finding a secant of that angle, the output of arc cosine. Okay. So this little trick is going to come in handy later on when we start trying to do more complicated calculus kinds of things. So make sure you practice it a little bit on the homework. Well, of course, you're going to practice it on the homework because all you guys do your homework. Any questions, actually, before I move on? Okay, so we've kind of just been doing algebra or trigonometry so far, we need to also think about calculus since we're in calculus 2. So let's try to take the derivative of arc sine. And in order to do this, we have to think back to, I guess, section 7.1 again, like we were earlier when we were talking about one-to-one functions. We know that there's a formula for the derivative of an inverse. Let me remind you what that was. We haven't had to use it a lot since then. So if I want to find the derivative of an inverse function, what I do is I divide by the derivative of the original function with the inverse plugged in, like this. So I'm plugging the inverse function into the derivative of the original function. And in this particular case, we're doing arc sine. So the function f is just sine x. And then the inverse function is arc sine. So let's start plugging this stuff in to the formula that we learned in 7.1 to see if we can work out the inverse for arc sine. Okay, so first of all, what is the derivative of f? What's the derivative of sine? Anyone?
Cosine.
Cosine. Good. So we're going to take a cosine function and plug in arc sine. In the denominator, and the numerator is just the number 1. In order to handle this cosine of arc sine, we have to think back to the Pythagorean theorem that tells us that sine x, or sine squared x, plus cosine squared x is equal to 1. So what I can do is rearrange this formula from the Pythagorean theorem so that we have cosine on one side and everything else on the other. I'm sure you've done this before. You would subtract off sine squared and then take the square root. So you get 1 minus sine squared underneath a square root. So why do I not need to think about plus or minus on this square root? Any ideas?
Depending on where it's located determines its sign.
Right. So remember for cosine, we're going to be talking about the upper half of the circle for now. So that'll always correspond, or excuse me, I'm getting this a little bit backwards. I'm thinking of cosine, but we're talking about sine. And remember, when we're talking about sine and arc sine, we're actually only talking about the right half of the circle between minus pi over 2 and positive pi over 2. So we need this half of the circle. And it looks like I need a pen with ink in it. So we're talking about the right half of the circle when we're talking about arc sine. And cosine values over here are always positive, or at least non-negative. So that's why we don't have to worry about the minus part for cosine, which corresponds to angles over here. Okay. So now we'll take this from the Pythagorean theorem and plug it in for cosine. So instead of cosine, I'm plugging in arc sine of x here, where this x is. And that's all underneath the square root. Still have a 1 on top. And now we can use the fact that sine is the inverse of arc sine and vice versa. So those two actually will just disappear. The sine and the arc sine will go away. All that is going to be left is the input x, and then that's getting squared. So what we're left with is the square root of 1 minus x squared in the denominator. And then 1 up top. Okay, so that's how we find the derivative or derive the derivative. Let me, over here on the left, where I have some space, or maybe just on the back of this page, let me write those two rules down. The way that your textbook does. Let's see. So I want to write it in terms of the chain rule, essentially. So instead of having x plugged in, I'm going to have some function u. And then we get two rules, or I'm going to tell you two rules. The derivative of arc sine with u plugged in. And remember, the domain of arc sine is between -1 and 1. That's why I have this extra bit up here, that my function has to be between -1 and 1. Then the derivative of this guy is what we just discussed, but with a u plugged in. So 1 minus u squared with the 1 on top. And then from the chain rule, you would get a du dx afterwards. So you have to take the derivative of whichever function you plugged in. And then I also want to tell you the derivative of arc cosine. We didn't actually work out all the details on this one, but it's really similar to what we did for arc sine, so we don't really need to. The only difference is that there's going to be a minus sign in front. Oops. And then this should be a u, of course. So we get minus, and then this 1 over the square root of 1 minus u squared. And then a du dx. And since we know the derivative of our functions, we also know how to do the opposite, the integral. We just have to, or we know how to find the integral of this guy. We just have to reverse the order. So if I integrated this side, I would get this side. If I integrated that side, I'd get an arc sine. I'm going to write it in a way that's going to be more useful to you guys when it comes to the exercises. Instead of a 1 minus u squared in the denominator, I'm actually going to put an a squared minus u squared in the denominator. Because often in the homework problems and in real world problems, you're not going to find just the number 1 here by itself. You might find some other number. And this is going to help us deal with that situation. So what we're going to get is a sine inverse, an arc cosine. Excuse me. Sine inverse is arc sine, of course. And then u, the variable, but now it's going to be u divided by a instead of u by itself. And then there's this technical detail that I need to include, that u squared should be less than a squared. And this goes back to the fact that the value of u should really stay between -1 and 1 here. But when I have an a squared, it needs to stay between minus a and positive a. Okay, any questions? Looks like this is going to be our stopping point for today, and tomorrow we'll get some practice using these three new rules. So are there any questions as we end?